Proof. So if G is summation k equal to 0 to m plus n ck, where ck is summation I equal to 0 to k ai b I minus k I k minus I. Yes. So suppose if G is primitive, suppose if G is primitive, that implies the ideal they generate is contains 1 C0 to Cn plus n, that contains 1 but C0 to Cn plus n is sits inside the ideal and therefore therefore 1 belongs to the ideal this implies f and g are primitive. Conversely, suppose f and g are primitive, we have to show that if g is primitive, that is the ideal they generate, it is 1. If g is not primitive, then there is some maximal ideal m belongs to max spec such that the ideal they generate is contained in M. Now, in the ring A mod M, if G bar equal to 0, the ring A mod M is. Since A mod M is field, A mod S is domain. This implies f equal to 0 or g equal f bar equal to 0, g bar equal to 0, thus either f bar equal to 0 or g bar equal to 0. This implies the ideal a0 dot 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 n is contained in M, or contradicting the fact that F and G are primitive. Therefore, Fg is also primitive. This proves this problem. Okay, so if you see the problem number 3, this problem number 3 says generalize the result of the exercise 2 in the several variable polynomial. So I think I may left the generalized case of this for as an exercise. I am not going to prove everything. It is left as an exercise. For the generalization of 2, 4 in several variable case. Okay. Okay. So then I left the problem 5, 4 partially. I have shown that M is generated by M contraction and X. Here is the problem first. I have okay. I have shown that M contraction and X generate the ideal, but M contraction is a maximal ideal. I am not unable to show that. If you recall the proof from the previous class, no, 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 it's not this one. No, not this one. Okay. Oh my god. Just realize. Okay, so here is the proof. I have postponed the proof that M contraction is a maximal ideal of A. I have proved the second part in some other way. I have defined the map and proved that it is a maximal ideal, then both of them are same. Blah blah blah. So I am giving the new proof. I mean the proof is exactly almost the same. Okay. I am directly claiming that M is generated by M contraction and X. It is easy to see that M contraction and X, the ideal they generated is in M, as X is in Jacobson radical of X by 5, 3 by the previous problem, and M contraction is a subset of it. So this this part is fine. Now the reverse inclusion. Let if is in the M, the maximal ideal. Okay, so by definition, the zero constant coefficient lies in the FM. We are done basically. Okay. So let if equal to summation ai xi I rounds from 0 to infinity is in n. So in A0 is in n by definition. The contraction A0 is in m contraction, and if is written as A0 plus x, A1 plus A2 x, A2x plus dot dot dot. Therefore, the whole thing, therefore, if is in the ideal generated by this implies M is in the ideal generated by this. This implies these two are same. Now, to take the quotient. Now, a x quotient 10 is filled since M is maximal ideal. As now, this M contraction of X is filled. Now, first quotiented by X, and then okay, let's go step by step. First quotiented by X, then quotient. This is just third isomorphism theorem. Now this is A and this is the image of the ideal here. It's filled. It implies M contraction is in the max pair. And we are done. And we are done. Okay. We have done this, we have done this. It's if it's quasi-compact is done. Okay. So the spec ZX is left. We will do spec ZX in later. Okay. This problem. Okay. This problem. Oh, okay. So we have done this one. We have done this part. So 2, 3 first part and the 4 is left. Okay, let's do it. Let y subset of x be a irreducible set. Consider the set z subset of y subset of z, and z is irreducible. Then S is non-empty as y is in S. Take the standard set inclusion as partial order on is, so we are planning to use John's lemma. Let y lambda y alpha alpha belongs to lambda be a chain. We claim that uh, okay, not y lambda, z alpha. We claim that z equal to union z alpha, alpha belongs to lambda closure is irreducible. If not, then z can be written as C union D, where C and D are proper closed subsets of Z, since Z is closed in X, C and D are also closed in X. Now, okay. So now note that Z alpha can be written as Z alpha intersection C union Z alpha intersection D. Now they are closed in Z alpha for all alpha is in lambda. Since Z alpha intersection C and Z alpha intersection D are closed in Z alpha and Z alpha is irreducible, implies Z alpha equal to Z alpha intersection C or Z alpha equal to Z alpha intersection D. What this implies? This implies Z alpha is in C or Z alpha is in D. Okay, so for all alpha belongs to lambda. So it may happen that for some alpha, Z alpha sits inside C, for some alpha, Z alpha sits inside D. But we will see that that will not happen. Either all of the Z alpha sits inside C or all of the Z alpha sits inside D. Okay. Our next goal is showing that. Okay. Now that should be the next observation. Okay. Observe that union of Z alpha or union of Z alpha Z alpha maybe in C, maybe in D. So I am claiming that either whole of the union is in C or is in D. If not, then there exists lambda 1, lambda 2 is in lambda, such that Z lambda 1 just a minute. Oh, Z alpha not in C and Z lambda 2 not in D. Without loss of generality, we may assume that Z lambda 1 is subset of Z lambda 2, since Z alpha belongs to lambda is a chain. So either Z lambda 1 is in Z lambda 2 or Z lambda 2 is in Z lambda 1. Okay. So if this happens, okay, so now Z lambda 2 it's not inside D, that implies Z lambda 1, Z lambda 2, that implies Z lambda 1 not inside D. Which is a contradiction. Means Z, both of them not in D, that's a contradiction. One of them has to be in D. Therefore, either union Z alpha belongs to lambda is in C, or union Z alpha belongs to lambda is in D. So, okay. Therefore, their closure is in C closure, or union Z alpha belongs to lambda is in D closure. But this is equal to C, this is equal to D. As C and D are closed in X, as C and D are closed in X, so that implies that okay, what is my notation? That implies Z. That implies either Z is in C or Z is in D. Okay, this is a contradiction. Okay, you may say contradiction, or otherwise this implies Z equal to Z, Z equal to Z. So, no problem. Therefore, Z is irreducible. Therefore, the chain has an upper bound in S. Of course, Y is in Z. This implies by John's lemma S has a maximal element. And we are done. And we are done. It is a maximal element, is an irreducible element that contains Y. So we got an maximal irreducible subset containing Y. And we are done. We are done. So problem number 2 is done. Okay, problem number 3. Let X is in X, then is irreducible, trivial. This implies subset of Zx, where Zx is a maximum irreducible component of X, is a irreducible component of X containing singleton X. Therefore, hence Zx. Then this covers the whole set. We are done. We have done this. Go to the next page. 4. Check that VP are irreducible. Is irreducible. Are irreducible for P is in spec A. Try to check that VP is a irreducible set. So we need to find the maximal irreducible subset. Okay, let y subset of spec A be a irreducible component of spec A. Then they are closed, right? Then y is closed. This implies y is equal to VA for some ideal A of A. This implies y equal to VA contains in V0. This is equal to V of root 0. This is union of VP. P belongs to spec A. P is minimal. This implies y has to be equal to VP as both of them are irreducible. This completes the proof. Okay. So we have done this, we have done this part also. So problem number 5 and problem number 3 is left. We'll do these two problems. Problem number 3. Okay, problem number 3. So recall for any subset y of a topological space X, y closure is the smallest closed set containing y. So note that note phi star of VB closure is already closed. So in order to show the equality, phi star of VB is contained in for some ideal A of A. Wish to show that VB construction is contained in V of A. Then this proves that it is a close. It is equal to its closure. Now phi star of VB is contained in VA. This implies VB is contained in phi star inverse of VA. VB is contained in, so phi star inverse of VA is V of A extension. V of A extension by 2. This implies a radical of A extension is contained in the radical of B. This implies, okay, since A extension is contained in radical, is contained in root B, since not since, root B. Now take some x's in A. That implies, by definition, phi x is an extension. That implies phi x is in root B. By the equality, this implies phi x n is in B by definition. This implies phi x n is in B. This implies x n is in the B construction by definition. This implies x is in the root radical of B construction. That also follows from by definition. This implies the ideal A sits inside the root B complement. Take the V of y of its contraction contained in V of A. Now V of B is same as V of B contraction contained in V of A. Again, B contraction extension is contained in B, so that V of B is contained in B contraction extension. This is same as phi star inverse of B contraction. We show phi of VB contained in V of B contraction is contained in V of A. Yes, that implies V of B am I doing it correctly? Yeah. Yes. Oh, just a minute. Ah, we have. Oh, we have done that. We have done that. Yes. We wish to show this. We have done this. Therefore, therefore, 5 star of VB closure is V of B contraction. We have done that. Okay. Problem number 5. If phi is injective, this implies kernel phi is trivial. This implies phi, but the ideal zero contraction is the ideal same, since 5 star y closure equal to 5 star of V of 0 closure, V of contraction same as V0 is in spec. Therefore 5 star y is dense. So 5 star y is dense in spec. Conversely, 5 star y is dense in spec if and only equal to spec that is same as V of 0 if and only V of kernel phi equal to V of 0. That implies root kernel phi equal to root 0 equal to root 0 if and only if root kernel phi equal to, what is our notation, nil radical. This shows that kernel phi is contained in nil radical. So this proves this part. Oh, okay, okay. So up to this part, we have proved it. So we have proved the problem number 22 for the case n equal to 2, and the rest, the general case is left as an exercise to use induction to prove. It can be proved directly mimicking the same proof, or you can use induction. What is left in the converse part? That 1 if and only if 2. 2 implies 1 is fine. That follows from the previous part. But 1 implies 2 is not proved. So we are now going to prove 1 implies 2. Suppose spec A is disconnected. This implies spec A equal to VA union VB for ideal A and B of A. Also, VA intersection VB equal to empty. Okay, so what is VA intersection VB? VA intersection VB is V of AB. So V of A intersection B is V of AB. That is equal to 5. That is same as V of 1 equal to, that is V of 1. And V of A union V of B equal to spec A implies, what is V of A union V of B? This also implies V of AB equal to the full space. Oh no. Oh no. No, no. V of A intersection V of B, V of A plus B. This is same as V of AB. Equal to V of 0. So this implies 1 is in the ideal A plus B. Since 1 is in the ideal A plus B, 1 can be written as like this: x is in A, y is in B. Then the V of A is contained in V of some x power k with obvious reason, and V of B is contained in V of y power k for k greater equal to, okay, we may take 0, no, we have to take greater equal to 1. This implies spec A equal to V of x union V of y. Again, 1 equal to x plus y implies phi equal to vx intersection vy equal to v of x power k intersection v of y power k for all greater equal to 1. Now xy is in the ideal AP. That implies hence A, which is isomorphic to A mod 0, is isomorphic to A mod the ideal generated by xy power n, is isomorphic to A mod A mod x power n by CRT. See that, okay, where it is? This one. This one and this one jointly implies that you can use CRT. Therefore, spec A is disconnected implies A equal to A1 plus A2. And how do we done? Now we are almost done. Now there is one problem left, 23.4. 23.4. That X is a compact household space. Root 4. Have already shown that spec A is compact for any commutative being A. Okay, so the only thing is left to show that the spec A is house dot. Okay, let's prove that spec A is house dot. Let P comma Q belongs to X and P not equal to Q. Then choose if belongs to A, if not equal to 0, 1 such that if is in P or if is in P and if not in Q, or if is in Q and if not in P. If is in P, this implies 1 minus f cannot be in P. This implies P is not in that set. This implies P is in the set x of 1 minus x. Again, if not in Q implies Q not in V of f. This implies Q is in x of f. Okay, since 1 equal to f plus 1 minus is applying V to both sides, This is empty. V of f. Again, f into 1 minus f equal to 0, applying v both sides, it is v of 0, that is full space. Now put the complement. Xf intersection x of 1 minus f equal to 5. So we have proved that. So we take P and Q, different element. We have found two basic open set, x of 1 minus f and xf, and they don't intersect at all. Therefore x is Hausdorff. Therefore x is Hausdorff. Complete. Check the proof. If you have any problem, please ask. Okay, so we have almost solved all the problem. The only problem left is showing the classification of spec zx, which I am not going to do in that class. I will send the proof. This is a huge proof, and I am not going to do that in the class. So classification of spec zx is left, and the problem 27 and 28 about affine algebraic varieties. So for these two problems, we need to wait till localization to prove all these problems. Till now, we almost solve all the problems.